Okay, let's continue to study the topic beam on elastic foundation. So, problem description is like this. We have a beam and this is placed on the elastic foundation which behave like a spring. This is elastic foundation. And there's going to be a transpose loading, some loading P or transpose distributed loading Q. Right? And when we have a loading at x equals 0, P0, x equals 0, and domain is infinite in x direction and minus x direction, we derive the displacement minus P0 alpha 2k E alpha x cosine alpha x minus a plus sine alpha x This was the solution, right? First, we made the carbon equation by modifying the carbon equation of Euler beam theory, and then we solved that carbon equation by applying also boundary condition. And this was a final result, you remember? Okay, so this is solution. We should remember this is solution when loading is applied place at x equals 0, right? So today's topic is extension of that Green's function approach. For general load Q. So today I like to talk about the solution, how to calculate solution when general shape of distributed loading is applied for the infinite length of the beam on elastic foundation. Okay, now let's think. Here x-axis, this is y-axis. Let's think that load is applied here, P, at x equal A. Let's say this is PA. Load PA is applied at x equal A. Then what's going to be a solution? So this is a solution when the load P is applied at x equals 0. So only difference is the position, the force at force is applied, right? So if we shift that solution, we can find out. So let's say that is a BAX equal minus PA alpha 2k e minus alpha x minus a. Just we can put x minus a instead of just x, right? This is just a shifting of coordinate in x direction. Cosine alpha x minus a plus sine alpha x minus a. Very simple, right? Very small change, right? Okay, then next, let's say the PA is applied at x equal a, and the other load PB is applied x equal b. So two load is applied. Okay, then similarly, we can calculate also VB, right? VBX is a very similar. So minus 2k PB alpha E minus alpha X minus B and something, right? So we just put x minus b instead of x, right? Then when we have two loadings applied, let's say that is a solution BAB. What can I calculate that? This is a linear analysis. So if we sum both solutions, then that's going to be solution for this case, ax plus bx. Very simple, right? So we use superposition theory. Superposition. Okay. We can superimpose the solution of each case, okay, in linear elastic case. So now let's generalize this simple idea. Y x, and let's say here x equal a, and load P, unit load P equal 1.0 is applied, and then let's define some function g is a function of x and a. X is a spatial point, and a is a point where no external load is applied, equal minus alpha 2k e minus alpha x minus a, and cosine alpha x minus a plus sine alpha x minus a. What's this? This is a displacement. At x due to unit load at x equal a. So this is the function g is this give you the displacement at x equal a due to unit load at x equal a, right? This is a green function. We are saying this is a green function. Green's function. And now let's consider very general case. P1 is applied at x equal a1. P2 is applied x equal a2. And Pn is applied x equal a, let's say pi. Pi is applied x equal pi, right? Very general case, right? How can I calculate the solution? Solution is can be calculated by superposition of each solution, right? So sum I equal 1 to n. N is a number of point load, and pi g x ai, right? So pi is a magnitude of load, because here the green function is defined by unit load. So if we multiply the magnitude of that load, this will be a solution. Okay, then next, let's consider little bit complicated case. Let's define some distributed load. This is a Px. Okay, let's Qx. Qx. From A to B. How can I calculate the response? By using the green function. So Bx equal integration from A to B, PQA QA GXA dA, right? So for the general case of loading, we can calculate the displacement by using Green's function, which is specially defined by the it derives from the solution of the unit load case, right? Okay, we are using this kind of approach for many cases, many engineering applications, fluid mechanics and solid mechanics too. So the concept is very simple. It can be Green's function approach can be used for linear analysis case. So first we calculate the solution. So for example, let's say this is domain. So first we calculate the solution for when the unit load is applied unit point load is applied here, and then we know the solution, right? And then we can use that solution. So, okay, let's say this is x and y position. Then we can use that solution is a function of x bar, y bar, x bar. So we can make generalize that solution with a green function. Then if we use this for like this, if we integrate the solution, we can calculate some general loading and solution when general load is applied. So this is a very well-known approach. Okay, any question? Okay, so now we studied, until now we studied the bar problem. It's a stretching case, and then bending problem, beam problem, right? Today, I'd like to introduce the torsion, which is a twisting problem. The member is twisted. The theory is more complicated than the bending and stretching. Okay. Torsion of prismatic bar. So this is today's subject. So the simplest case is a circular shaft. Torsion member is very widely used, right? To deliver the torsion, right? You know, the automobile, there are torsion bar, lot of torsion bar is used. Okay, so case of torsion is like this. So we have a shaft. This is a shaft, and of length L, and x-axis. And moment, torsional moment, mx is applied, and mx. This is torsional moment is different from bending moment, right? You know the difference between bending moment and torsional moment. And let's consider the section. This is section g-axis, y-axis. And let's say the radius equal r. And let's consider some part of the cross section, this one, R, and this is a dr. cylindrical coordinate system can be defined by the radius and angle theta. Let's say this is theta, d theta, okay? So the small part of can have a dimension dr and r d theta. In this case, let's consider strain xx. If we twist the circular bar, what happens? Displacement in x direction. There is no displacement in the longitudinal direction of this bar, right? So this is 0. Strain xx is 0. And then how about strain rr? Strain in here circumferential direction. Okay? Strain rr. Strain rr is radial direction. Radial direction. This is strain rr. This is radial direction. Strain rr. So even when you twist this, the radius doesn't change, right? So strain rr is 0, and strain theta theta. This is the direction of circumferential direction. So this is 0, 2, and Rx. Shear strain Rx. Shear strain Rx. This is 0. So in that case, also shear strain R theta is 0. So all the strain is 0 except for strain x theta is not 0. So in this circular beam case, circular bar case, we need to consider one shear strain. It's about x-axis and z-axis. So let me identify that strain. What's the shear strain? Shear strain gives us geometrically the change of angle, angular change between originally the original two vector. So let's say this is undeformed, and let's draw a line in undeformed situation, and then let's give a torsion here. Then this line will be moved to here. This is deformed, undeformed, so original. This is deformed. So theta is this direction, right? This is theta direction, and this is x direction. So originally these two vector, this is the original vector, and is changed to this vector and this vector. It means their angle is changed. This is change of angle, right? Angle is changed. So angle change. Angle change. This is the angle change, gamma x theta. This is the gamma x theta. Gamma x theta. And let's think this is the length of this bar is dx. dx. And this is a beta. Beta equal angle change beta equal gamma x theta. This is equal dx r d. Okay, so I need to draw one more picture. Let's draw a curve. Okay, this is the original line, and this is rotated line, the deformed line, and okay, this is a pi d. This is d pi, and how about this is a r, and this is a r d pi. Then angle, rotation angle equal gamma x theta equal dx r d pi. Right? So here this length, what's the this length? This length equal beta dx, right? And this length is r d pi. This is the same, right? Same. So we can calculate this relation. This one and this one is the same. Okay, so finally, strain is an angle change dx r d phi, and here let's use a material law. Tau x theta equal g gamma x theta equal g r dx d pi. Here r is a range of r is this. Okay. So in this case, we should remember strain zeta x equal strain x zeta stress, and strain x zeta x equal strain x zeta, right? Because of symmetry of strain and stress tensor. Okay, we start from the displacement field, right? Displacement field of twisting of bar, right? And then we calculate the strain. Then now we obtain the stress. What's the next? If we know the stress, we can calculate the twisting moment, right? So this is R direction, right? Let's say this is R direction. Okay, so let's consider some part of here. This is R direction, R, and this is X direction. What's the stress? X zeta, direction of X zeta. Stress, direction of strain X zeta. What's the direction of strain X, stress X zeta? This is X direction. So we can define, this is a zeta direction. What's the direction of this stress? This stress exists in this cross-sectional plane. And what's the direction? Direction is R, zeta direction. So direction of that stress is this. This is a stress x zeta. Okay, something like that. And this is area A. So moment x can be simply calculated by integrate that stress x zeta, and from here to here R is your arm, the moment arm, RDA. This is a relation between stress and moment, right? This is reduction formula we learned months ago. Then here let's put the previous result, GR dx d pi, and this equation become A GR square dx d pi dA. Okay, then that equation become G is constant, and let's assume this is constant too, R d phi. right? Actually, this is constant too. And then we have only, so this is about the, right? This is not about the cross section. And this is not about the cross section, right? So this is both are constant on cross section, right? Because pi is a function of x, g is a material constant. So only remaining thing is this one. R is changing on the cross section. And we are saying this is a J and polar moment of inertia. So that's the geometrical constant. It depends on the geometry of shaft. So in the circular cross-section case, J equal 2 pi r 4. So from that equation, we can find out mx equal g dx dy and j. And finally, dx dy equal g j mx. The left hand side, change of twisting angle in x direction, right? This is change of twisting angle. Is proportional to the mx over gj, right? So gj will be some resistance factor for the twisting. If j, the value is big, the member can resist more than smaller case of j. And g is also, mx is a twisting moment. Okay, mx is a twisting moment. Okay, and stress zeta x zeta will be mx j r. These two equation is important. Okay, this equation gives us relation between twisting moment and torsional moment and stress. If we put this equation into here, you can find out that equation, right? Right? Here, if we put that equation into here, let's say, stress etc. equal g r dx d pi. Right? So in beam bending case, stress xx was minus m I y. Right? Very similar, looks similar, right? Beam bending. So compare both equations. Very similar, right? M is a bending moment. I is the second cross-sectional inertia, and Y. Very similar form. Only difference is I and J and R and Y and the type of moment. Special case when dx, d phi is constant. The rate of twist angle is constant. For example, this is a constant case. Moment m is applied at the tip. This is the case. This is a constant d phi dx. Y. At the all the beam cross section, this is a torsional moment is the same, right? This is a torsional moment is the same, right? At this section, torsional moment is m. In this section, torsional moment is m, m, m. So, because the torsional moment is same, here in this equation, this become constant. And the other case is this one. We have a distributed torsional moment. Let's say this is a m. Okay, in this case, the torsional moment looks like that, mx, right? Torsional moment is changing, right? It means non-constant d phi dx. In this case, the change of twisting moment is not constant, right? This is a little bit complicated case. Now let's consider this case. Constant change of twisting angle. Okay. So in this case, okay, delta pi equal gj mxl and mx equal l gj delta pi. We are saying this is a torsional stiffness. Right? So, when the G, the shear modulus is big, torsional stiffness is big, right? This is very reasonable. J is big. J is big means the R is big, right? In this case, J is big, right? If the radius of the circular solid circle is big, and also if length of the shaft is long, it can be very easily twisted, right? So torsional stiffness become smaller. Okay. Any question?